So we've talked about this phenomenon before. As an allele becomes rare, a higher and higher percentage of that allele is found in heterozygotes. In this case, where you've got the rare allele at a frequency of 0.3, 30% of those alleles are found in homozygotes, 0.3. In this case, where this frequency is down to 0.1, only 10% of those A2 alleles are going to be found in homozygotes. In this case, where the frequency of the A2 allele is down to 0.01, 1%, only 1% of those alleles are going to be found in homozygotes. So the rarer a allele gets, the less likely it is to show up in a homozygote. What this means is that if an allele is recessive and rare, selection will hardly ever see it. In this diagram here, these are if A2 is completely recessive, if A2 doesn't affect the phenotype of an individual. The only time selection will see it ever is when it shows up in these individuals. That happens 30% of the time. Okay, so if this A2 allele is harmful, 30% of the time it'll show up. Natural selection will see it and it will get swatted down. That means it's going to become rarer. Maybe it's going to drop to a frequency of 10%. Okay, here it is at a frequency of 10%. Now natural selection only sees these alleles, these harmful alleles, 10% of the time. It still swats them down when it sees them, but it's getting to be a much weaker force. It's changing the frequency of the A2 allele much more slowly because it just doesn't see all these alleles that are here in light green. Okay, as the frequency of the A2 allele drops even farther, remember selection's still beating on it, it gets lower and lower and lower until basically natural selection very rarely sees the last few alleles in a population. At first, when you have a harmful allele that's at really high frequency, natural selection will hammer it, and you'll see the frequency drop really quickly. But it can take an extremely long time for natural selection to get rid of the last few harmful alleles in a population. What does this have to do with positive assortative mating? Well, imagine a population that has some of these harmful alleles floating around in it. Natural selection has trouble removing them because they're recessive, and because they're harmful, and because they are rare. Okay, but what happens when close relatives mate? To go into more detail about inbreeding, I'd like to talk about this little animal. This is an animal called a naked mole rat. These are very strange mammals that live underground in Africa. One of the notable things about them is that they are incredibly ugly, so ugly that in fact they seem to have come around the far side of ugly and gone back into being cute again. They look basically like somebody took a bratwurst and put some buck teeth on it. And the people who study them are really quite fond of them because they are basically the dorks of the natural world. They also have an extremely strange social structure. And one of the things that's strange about it is that these naked mole rats frequently mate with their close relatives. Aw, that's a face only a mother could love. So what happens when close relatives mate? Well, what you have here is a mating between half-siblings. These two individuals share one parent in common, and they mate and they have an offspring. What could have occurred in this case is that this parent here donated the same physical allele to both of these offspring, and they both donated to this individual down here. That is, these two alleles that this individual inherited came from the same physical stretch of DNA just 2 generations back. Okay, the probability of this happening for any given locus in the genome is 1 out of 8. that means that 1 out of 8 genes in this individual down here must be homozygous. And the funny thing is that that's true. This individual must be homozygous for those genes, no matter how rare the A1 allele is in the whole population. Okay, this is called the inbreeding coefficient. It's usually denoted with this big letter F. This number changes depending on exactly what kind of inbreeding mating you're talking about. So for example, for first cousins, it's pretty small, it's 1/16. For mating between a parent and offspring, it's 1/4. For mating between full siblings, it's 1/4. So when you're talking about matings between close relatives, and this is what I want you to take away from this, you're talking about somewhere between, 1/16 or 1/4. For second cousins, maybe 1 out of 32. Okay, now let's think about how likely it is that an inbred individual is going to get 2 copies of a rare allele. There are 2 ways to do it if you're inbreeding. And let's take the example here. We're going to look at the offspring of full siblings. Remember that their F is equal to 1/4. So there are 2 possibilities. For any gene in the genome, there's the possibility that this inbred offspring got 2 copies of the exact same physical allele because of inbreeding. When that happens, we refer to those alleles as being identical by descent, or IBD, identical by descent. Well, what's the probability that an offspring of full siblings gets 2 copies of the same allele because they're identical by descent? It's F. Okay, the inbreeding coefficient. The probability that the offspring won't for any given locus is 1 minus F. Now, I don't want you to walk through this whole probability tree. It's not one of the ones you're going to have to reconstruct in an exam. I just want you to see how this works out. If that offspring got 2 alleles that are identical by descent, what are the odds that they're the rare allele, the one that has a frequency of Q? Well, you know they're going to be the same allele. With a probability P, it's going to be the A1 allele. With probability Q, it's going to be the A2 allele. Okay, so this is one way of getting 2 of those rare alleles in an inbred offspring. The other way is the same way that outbred offspring might get 2 copies of a rare allele. From down here, it's just the usual p squared, 2pq, and q squared that you're used to. Okay, so if the offspring doesn't get 2 alleles that are identical by descent, well, then there's still the possibility that mom happened to have one of these rare alleles, and that dad just happened to also have that rare allele. Not because of inbreeding, just because of dumb luck. Okay, so that's the other way of getting 2 of these rare alleles. So altogether, if you have an inbred offspring, the probability it's going to end up with 2 of these rare alleles is going to be Q times F plus Q squared times 1 minus F. Why is this so harmful for inbred offspring? Well, let's take a look here and we'll compare inbreeding to a case without inbreeding. So this is over here is a case where the parents were not at all related. Here's a case where they were related to some degree. And remember that, relevant values for this are somewhere between 1/4 and a 1/16, maybe at 1/32. Okay, often what I will do when I'm trying to understand a situation like this is I will just sort of plug in numbers and work out the math and see what it looks like. But here's another way in which you can approach questions like this. Okay, is instead of working out the math, just kind of get a rough idea of what's going on. Let's suppose that we're dealing with full siblings, so F is equal to 1/4. Let's suppose we're dealing with a really common A2 allele. Let's say the frequency of it's 1/2. Okay, so Q is equal 1/2. Well, this is 0.5 times 0.25. I know that this is 0.75 times 0.25. Okay, I know that much, but I'm actually not going to work out the rest of the math. I know this is 0.25. I'm just going to leave it there. Huh. Okay, well, these are all sort of the same order of magnitude. Everything over here is on the order of 10 to the minus 1. This term is, so when you add them together, you're still going to have something on the order of 10 to the minus 1. And over here, again, yeah, you've got something on the order of 10 to minus 1. Okay, I'm not going to go through and take the time to figure out exactly where they lie. We just know that they're roughly similar. Okay, so when Q is high, when an allele is common, the odds of an individual ending up with 2 copies of that allele are hugely influenced by whether you're dealing with an inbred offspring or not. But what happens as Q starts getting smaller? Okay, now you've got 10% in there. Okay, this is still in the order of 10 to the minus 1. Oh, this one dropped. This one's now down at the order of 10 to the minus 2. Huh, and this one's on the order of 10 to the minus 2. And when you add these two together, this one stays at the order of 10 to the minus 1. So this whole term over here is still somewhere around 10 to the minus 1. Whereas this one has dropped to a lower order of magnitude. So what happens if we go down even farther with Q? Now Q is at a frequency of 10%. Okay, this one's at least dropped to 10 to the minus 2, but wow. Q squared is at an order of magnitude of 10 to the minus 4. Now when you compare inbreeding to outbreeding, the odds of getting 2 of those rare alleles is something like, it's around 1 out of 100. It's on that order over here. Over here, it's an order of 1 out of 10,000. This is a 100-fold difference. And now we're actually getting into the range of serious genetic diseases. For serious genetic diseases, for reasons we'll get into in a later lecture, frequencies of those alleles are usually down around 1 in 1,000. They may be a little more common, a little rarer, but these are usually what we see. Okay, this is a small term. It's on the order of 1 out of 1,000. But this one is on the order of 1 out of 1,000,000. And so is this. Okay, now the probability of getting this disease, if this is a disease-causing allele, is something like 1 out of 1,000 for inbred offspring and 1,000 times lower than that for outbred offspring. Now, it might not seem to you that 1 out of 1,000 here is such bad odds, but there are a lot of genes in the human genome. And for each one of them, there can be really harmful alleles floating around out in the population at a low enough frequency that natural selection cannot detect them. It is very likely that any offspring of close relatives is going to get at least a few double copies of harmful alleles at some gene in the genome. Okay, over here for this individual, the odds of that happening are 3 orders of magnitude less. So basically, when you talk about mating between close relatives, it increases the odds of getting every genetic disease there is 1,000 times over what you expect for the normal outbred population.